Good evening. Today we will go over the concept of a triple integral, which is the last type of integral in this unit concerning functions of several variables. So take the time to write this down and sketch the, not much to sketch, but just a rough sketch of what would represent the domain of the function in question here. So let me go over a couple of preliminary aspects on this section. When you go over this section at this point, we assume, and I assume, that you are very well versed in the concept of a double integral. Okay, so how we actually define it, starting all the way with the partitioning of the domain for a function of two variables, which is a region in the plane. We call that domain D usually in these previous sections. The difference between how we compute the integral over rectangle domains or more general domains with Fubini's theorem and so on and so forth. So I'm saying this because at this point, once you understand very well how the double integral is constructed, we do not have to go to the same length of actually explaining how the triple integral is defined, because it follows really the same framework of splitting the domain into a partition of non-overlapping units, which in this case are little cubes. Obviously, it's the analogous to squares for the double integral. So the overall idea is the same. It'll be too tedious actually to go over all the details of constructing the Riemann sum, so I'll just go a little bit faster, or I'll cut some shortcuts essentially, and I only focus on the important key aspects that make it different from the double integral. So as with all integrals in this class, like I said before, we start by representing the domain and partitioning that domain. For simplicity, you can also think about the domain being a box, actually, a straight box, which is the simplest possible domain for a function of three variables with respect to the integration at least. So in fact, let's write this as a remark. Just as rectangle domains are the easy ones for the double integral, right? For a function of two variables, then straight box domains in 3D will be the corresponding easy domains for what we're going to call a triple integral. So, by the way, the notation, we can already establish it right now, is using three integral symbols. Just like the double integral, you're going to specify the domain, which is denoted by E in this section, and of a function of three variables, and then the unit of area becomes the unit of volume. So it's the formal notation is the triple integral over the domain E for the function f of x, y, z, dv. But going back to the construction of the integral, so just use your imagination as much as possible, right? Once we split the range, the corresponding range for x, y, and z corresponding to this solid into non-overlapping segments, when you impose that partition for all three x, y, and z, that will result in a partition of the solid in tiny little boxes. They will become tinier, of course, once you take the limit of the Riemann sum. But the typical piece of the split in the domain, it'll be, like I said, in the shape of a small box here. So actually, let me take it apart. Inside the domain E, you're going to have basically a box with the corners given by, well, let's say with the sides given by delta x, delta y, delta z, right? So if you imagine a partition over the x, y, z portions of the domain, delta x will be the difference between two nearby points, xi minus x minus 1, delta y will be yj minus 1, delta z will be zk minus 1, right? I have to use three different index, I, j, k, because obviously if you have all combinations possible, right, with these segments to make these little boxes. So imagine that this domain is filled with these boxes. So So for example, a typical one in the interior of the domain will look kind of like this. And the Riemann sum corresponding to this obviously is going to be a triple summation by the index I, by the index j, by the index k. And just like for any Riemann integral, you're going to pick an intermediate point on the box, which in this case we're going to call it xi star, yj star, zk star to identify it with the corresponding box. And you're going to evaluate the function at that point. Okay, so always the Riemann integral again always means function evaluated at an intermediate point in the Riemann sum to start with, right? At an intermediate point on the piece of the partition times the measure of the piece of the partition. That measure could be again dx, length of the segment for the Riemann integral from calculus 1, dA, the area of the little square from the double integral, and now is going to be dV, which will represent the volume of the little box. So the volume dV is going to, when we take the limit, right? So the volume of the little box is going to be delta x, delta y, delta z. Right? The volume of the little box times the function evaluated at the intermediate point. Okay, so suppose you have m pieces in the partition with respect to I. Suppose we have n pieces for the partition with respect to z. Let's say p pieces for the partition with respect to z. Okay, once we take the limit as m and p approaching infinity, provided this triple sum exists in the limit of this triple sum exists, this will converge to a quantity which will be called the triple integral of this function, and denoted, as I mentioned before, as the triple integral of f x y z dv. So in other words, this piece here will converge to what we're going to call dv, right? The volume of the what becomes the volume of that box in the limit as we take the limit of the Riemann sum. So anyway, without further ado, that's the overall framework, and I hope again you can see this in the context right now when you look at all the previous different types of integral you had before, because again the principle is the same, right? Partition, the measure of the partition times the function evaluated at the intermediate point. Obviously, in practice, we'll see how we can actually compute this integral, because we're not going to find these integrals via the definition. But let me actually point out a couple of important remarks, and they are indeed important to not make confusions between this and the previous integrals. So the first important remark I want to make here is that when we talk about the triple integral, we visualize, or let's say we sketch the domain and not the value of f of x, y, z, right? So not the actual value of the function at any point in the domain. Why? Because we are three-dimensional beings, so we basically can visualize anything up to the fourth dimension in the same coordinate system. So to put it simply, the three-dimensional coordinate system is occupied by the representation of the domain. The function evaluated at a point on the domain, it'll be the fourth value. So you have to basically put that, visualize that value separately if you really have to. But there is the consequence of this is that there is no default graph of f of x, y, z, or the default geometric meaning of this integral. There could be other meanings depending on the meaning of the quantity. It's not like the integral doesn't have a meaning. Remember, we do these integrals for a purpose, to solve real life problems, but there is no automatic graphical representation of the integral. In calculus 1, remember, in calculus 1 the integral from a to b of f of x dx would be the area under the or between the curve and the x-axis. In the case of the double integral, that meaning, default meaning, was a volume. The volume of what? Well, you look at the domain of this double integral, you look at the graph of the function of two variables, which was a surface, and as it turns out, right, the double integral will represent the volume between the graph of the function, which is a surface again, and the actual domain of the function of two variables. We don't have the same automatic geometric representation in this case, because again, there are four quantities. It's a four-dimensional analogy basically, so we cannot visualize it. Now you may wonder, okay, what is it good for after all? Well, it's good for many things, but the easiest example you can have in mind, that's always a default example if you want. Like if you always want a meaning of an integral that works in all dimensions, or not in all dimensions, but in the 3-dimension as well, you can think about density-like functions. Like for example, let's say the meaning of f of x, y, z is the mass, the density of the solid E at the point x, y, z, okay? Because in general, remember, the density varies with the position on the object. So in that case, to take the triple integral of this function dv is to, for each partition, is to multiply the density by the volume of that piece in the partition, which means that altogether, that's going to be the mass of that tiny piece of the partition. So therefore, the triple integral, which is nothing but a limit of a sum of these quantities, will represent therefore the total mass. So obviously, there are lots of meanings you can attribute, but again, not a geometric meaning by default. Now I forgot what was the second remark. I think I'll get to that at this point. But yeah, so that's the important aspect that I want to point out. The domain is a solid, right? Closed solid. It's what we sketch in order to compute the integral or to visualize the function itself. So we visualize the domain typically only, not together with the value of the function in the same coordinate system. Okay, so I think we can actually go straight to the computational aspects, again starting with the easiest possible domain, which is a straight box domain, and then we'll move on to more general domains and see how that works out. So stay tuned for the next page. All right, so analogous to the double integral, if the domain E is a box, which is to say all variables have constant bounds, let's say x between a and b, y between c and d, and then z between r and s, let's say. I don't want to use f because that's for the function itself. So if the domain is a straight box, then the triple integral is an iteration of simple integrals that you can compute from the inside out. So the iteration of several simple integrals, or one variable integrals, follow the same recipe as in the case of a double integral, except that you do it 3 times now because you have 3 variables to integrate. So again, the formal notation, always make sure you don't confuse the formal notation with the indication of how you compute this. And so on the right hand side now we're going to write down how we can compute it. And notice that the order, in the case of a straight box, the order of the integration doesn't matter. I'm not going to write all permutations because there's too many of them, but I hope you get the gist of it, right? So you can integrate it like that. That is to say, again, you always go from the inside out, in that order. So that means the first integral in this configuration will be with respect to z. First, followed by the integral in terms of y, and then in terms of x. And then any other permutation. So for example, you could also do CD, RS, AB, if you so desire. And sometimes you may desire that because remember, just like in the case of a double integral, switching the order of integration might make the problem easier. In this configuration, obviously the first one will be with respect to x, followed by the one with respect to z, followed by the one with respect to y, and so on and so forth. Right? So again, that's why straight boxes are the easiest, because you can just basically switch the order of integration at will without any problems. So without further ado, let's just compute one triple integral from top to finish. We're going to do more than one, but just one which involves a straight box domain. So in many problems, actually, you have the triple integral already given as an iterated integral. The function to integrate in this case is x plus y plus z, and the order is dx, dy, dz. Again, it may be important to extract the intervals for each x, y, z, so make sure you pair the dx, dy, dz with the correct bounds, right? So that means x is between 0 and 2, this was 1 here, right? So y between 1 and 2, and z between 0 and 1. Same mechanics. The only problem is that you have to go even slower in the beginning because there's more room of computation mistakes because you have 3 variables now to keep track. And now when you do the partial integration, right, from the inside out, you got to be careful to visualize the other 2 variables as constants, right? So one at a time, right? So very slowly in the beginning. So that means you can work on your own pace and pause the video if you want to check the work later. Because I usually don't take breaks, like I mentioned before, since you have the option of the pause button. So there's no reason to make the video longer than it's necessary. Okay, so dx first, which means y and z are constants. So the first antiderivative is x squared over 2 plus y x plus zx. And again, to avoid any confusions, write down the bounds and specify the variables for which those bounds correspond to. So that's for x between 0 and 2. And then when I'm done with this, the next integration will be with respect to y, and then after that with respect to z. Okay, so now I'm just plugging in 2 and 0 for x. So I get, let's do it with some extra steps. So I get 4 over 2, which is 2, plus 2x, plus 2y, sorry, plus 2y, plus 2z over here, minus plug in 0, that's 0 plus 0 plus 0. Let me write it one more time so I can see it better here. So now I have to integrate 2 plus 2y plus 2z in the order dy dz. All right, moving along, partial the integral with respect to y. Now z is a constant, so the antiderivative is 2y plus y squared plus 2zy. Again, z is a constant, so don't get confused with that. Now with y between the bounds y 1 and 2. Let's leave some room for plugging in 2 and 1. So it's going to be 4 plus 4z. And then minus plug in 1, that's 2 plus 1 plus 2z. Simplify further, we get 4z minus 2z, that makes it 2z, and then the constant is going to be 8 minus 3 plus 5. And finally the last integral will be z squared plus 5z between 0 and 1. That makes it 6. Okay, So that being said, once again, there are other things that are analogous to the double integral. And it's extremely important now to actually keep this in mind, because remembering this will make the computation even easier than what we just did so far. So if the function to integrate happens to be a product of functions in x, y, z, that is to say, and the domain is a rectangle. So let me illustrate one more time. Let's say the bounds, not rectangle, sorry, a box. Let's say the bounds are all constants, from a to b, from c to d, from r to s, and then like I said, the function to integrate happens to be factored in a function of x, a function in y, and a function in z. So if you can actually factor the function to integrate like this, which by the way in the previous example it's not possible, right? X plus y plus z, you cannot factor it into a product like this. So this is the to use the notation on the top of the page, this will be dz dy dx, right? Dy dx. So if you have if you have a domain in the shape of a box and you can factor this function to integrate in a product like this, then the triple integral becomes the product of three Riemann integral for the functions in x, y, z. So this will be the integral from from a to b f of x dx times the integral from c to d of g of y dy times the integral from r to s of h of z dz. Again, analogous to the double integral. That makes it again very easy to, very easy, all things considered, right? So let's put it here in a red banner here, so we emphasize that this is an important remark. It's definitely faster to compute most of the time because you don't have to integrate from the inside out, right? You can compute all three integrals at the same step. So let me illustrate with a quick example. Let's say you have to compute the integral from 0 to 1, from 1 to 2, from 0 to 3, and then the function to integrate is x squared y z third dx dy dz. All bounds are constant. The function can be split into a product of x, y, and z. So therefore, this becomes, again, make sure you pair the bounds correctly. This becomes the integral from 0 to 1 z third dz. Middle one goes with y. The integral from 1 to 2 y dy. And then finally the integral from 0 to 3 x squared dx. So just the power rule for all of them, z fourth over 4 between 0 and 1, y squared over 2 between 1 and 2, times x third over 3 between 0 and 3. So the first piece is 1 over 4, followed by 4 over 2, which is 2 minus 1 half, and then 27 over 3. Let's see, what do I get? 3 over 2, 27 over 3, 3 over 2, 1 over 4, 27 over 8. Okay, so as far as triple integrals are concerned, this is the easy part. So let's see how we deal with more general domains. Just like the double integral, we won't be able to integrate, we won't be able to have a formula for any type of domain. But if the domain has a certain shape, it turns out that we have a Fubini-like theorem corresponding to it that allows me to split the triple integral into a simple integral and a double integral. So that's why the double integral is so important, because actually, as you will see here, and later as well, it is part of the mechanics of computing other integrals. The double integral is used to compute a triple integral. It is also used to compute a surface integral toward the end of the term, as you will see later. So stay tuned for the next page. Okay, so let's take a moment again to sketch this. This is the best we could do by hand to just visualize the main concept of what we call the Fubini's theorem for the triple integral. So this is just a concept sketch basically, because you will see that in most of the problems the picture doesn't look like this one. This is kind of like a generic representation, but I think it still serves the main idea. Let me illustrate what we're trying to represent here with this sketch, and then you can try to replicate it on your notes. So this will be the coordinate system here. What I'm trying to represent here is the type or the shape of the solid. Okay, so this is like a solid, right? It's the shape of the solid that can be integrated via Fubini's theorem. This is the top of the solid here, over here, and then the bottom, right? So it should be a closed solid. It doesn't have to be in this kind of cylindrical shape, but that's the main idea. So Fubini's theorem states that we can split the triple integral into an iteration of a simple old-fashioned Riemann integral and a double integral, provided that a solid which represents the domain of integration has the following shape, described by the following type of equations. So the solid E, which is going to be the domain of the function to integrate, so the domain of f of x, y, z, needs to be represented by one coordinate between two functions of two variables. Essentially, geometrically, the solid should be between two surfaces with the same domain. So, for example, in this case, the solid E looks like defined by z coordinate between two surfaces, a bottom surface, let's call it u1 of xy, and a top surface u2 of xy. So the bounds of one of the variables can depend on two variables, provided that u1 and u2 have the same domain D in the xy plane. Okay, so in this picture here, imagine that on the top, this is the surface represented by the equation z equals u2 of xy. The bottom is z equals u1 of xy. So you kind of see how this goes actually. This will be the innermost integral, because it's like exhausting, it's like basically splitting the domain with this, let's say, thin spaghettis, if you want, right? That run from u1 and u2. As long as those two surfaces have the same domain, then the Fubini's theorem applies. So here in the middle, let's actually use a different color. I want to imagine that this piece here will be D, again, the common domain of u1 of xy and u2 of xy. Okay, so if I see the picture from above, and it clearly the two surfaces project onto the same domain in the xy plane, yeah, and like I said, in z belongs is between those two surfaces, u1 of xy, u2 of xy, then the Fubini's theorem can be applied. And the Fubini's theorem states the following, that again, this is the solid E, right, the whole thing. So the Fubini's theorem states that let's again use a different color to emphasize, the triple integral over this solid for the function f of xyz is dv is going to be the iteration between the innermost integral is going to be with respect to z, the variable in between those two surfaces, again with the bounds u1 of xy, u2 of xy, the function to integrate dz, and then the resulting answer, which is going to be in terms of x and y, keep in mind, right? Because once I do the integral with respect to z and plug in these bounds, this stuff here is going to be in x and y. And then the outermost integral is going to be a double integral over the common domain of u1 and u2. Okay, so that's what makes the problem sometimes trickier to set up, because if you don't have already the picture given, or the equations, or the bounds, in some cases the bounds are already provided, which makes it easy. But if not, you need to figure out what constitutes the top and the bottom in terms of these surfaces, the equation of the common domain, and then set it up like this. And then the problem still goes on with lots of steps. Assuming you do the innermost integral, now you end up with a double integral. How do you solve that double integral? Well, there's a Fubini theorem for the double integral, what we did before. Maybe you have to use polar coordinates. That depends on the shape of the domain, and so other things. Okay, so everything that is known from the double integrals is applied, or can be applied in this case. So another important remark: there are three versions of this theorem. We're not going to insist too much, but it's important to keep in mind, because I don't want to waste time to write so many. In fact, we can actually just write them down, because the solid can be along the z-axis, along the y-axis, or along the x-axis. So it can be along z, x, or y-axis. So just basically the same variation, except now, for example, if it's along the y-axis, then y is between two surfaces in x and z. So permutations of the same concept. So for example, if you have, let's say, y between two functions in the other two variables, x and z, I hope it's pretty clear that in this case, and again, these guys will have the same domain D, the domain in x and z, then in that case the triple integral will be obviously the split between a simple integral over the bounds of y, u1 of xz, u2 of xz, f of xyz, dy, and then the outermost integral will be a double integral for the common domain in x and z. Okay, so the domain for u1 and u2. And I'm not going to write the third one, but I think you get the gist, right? I mean, if x is between two functions of y and z, then you can set it up like this as well. So it is crucial, as a last remark before we turn to an example or two, to identify which is the innermost integral. Most of the time it's obvious. Sometimes actually you can kind of, you may have not a unique answer, because see, when I say u1 of xy, first of all, one of these can be a constant. So remember, a function in x and y doesn't have to contain automatically both x and y. It can be treated as a function in x and y, but it may contain only x, only y, or indeed it can be constant. Now, if both are constants, or every bound is constant, then you go back to a box. So that's pretty easy. But don't expect necessarily that both of them to depend explicitly on x and y. When they do, of course, the innermost integral is pretty obvious. So let's look it up at a couple of examples on the next page. Okay, here's an example. I forgot to change the color before I wrote it, but it should be fine. So here's a version of the problems you can encounter, right? So let's say I want to compute the triple integral of the function x squared sine of y. And the domain of it is defined by three ranges for x, y, and z. Okay, so let's actually write them one more time here. So let's focus on the actual ranges. And pay attention that the order they are given, sometimes the problem makes it easy and kind of gives you the bounds in the correct order, but here I purposely chose them in a kind of arbitrary order here, so I can point out how you can recognize which stands for the innermost integral and which one for the outermost integral. So remember, in the Frobenius theorem in this case, again, one of the advantages is that, of course, you don't need to sketch anything. Once the bounds are provided, you can just go straight away with the actual integral. Just make sure you put the bounds of the integrals in the correct order. So the innermost integral, remember, needs to have a variable in between two functions of the other two variables, right? Like that, u1 or u2. I mean, if you look at the bounds presented here on the left side, pretty obvious that in fact y actually has the bounds dependent on the other two variables. So y is the only one with bounds in the other two. Now what happens if all bounds depend on a single variable? Then in that case it doesn't really matter which one gets to be the innermost one. It is still true, even in the triple integral, that the outermost integral must have constant bounds. Now from Fubini theorem, remember, the outermost integral is a double integral, but how do we compute the double integral? There's a Fubini theorem for that as well, and when you split that domain as a type 1 or type 2 domain, or in polar coordinates, for example, in all cases, no matter how you set it up, the outermost integral will have the constant bounds. So with that, it's the order of integration should be pretty clear, right? So the triple integral in the problem, starting from the outside, outermost is going to be from 0 to square root of pi. Middle one is going to be from 0 to x for z, and the innermost from 0 to xz. Again, make sure you pair them correctly. dy, because y is between x and z, the middle one is going to be dz, and the outermost one dx. Okay, so this is the double integral. So basically in this setup, the outermost integral, it's like a type 2 integral, because z is the vertical axis and y is the horizontal axis. In any case, which one deserves to be type 1 or type 2 is not that important actually, right? I mean, the whole idea is who gets to have constant bounds on the outside of the integral or not. Okay, so always go slow to make sure your setup is correct. Usually this is the hard part, or the source of many mistakes. Indeed, many exam problems or test problems will only ask you to set up the bounds and then leave the computation, for example, to Maple. In our case, let's actually do the whole thing. So with respect to y, first, x is a constant, so let's integrate that one first. So we have x squared, the integral of sine is minus cosine of y, with y between 0 and xz. And then we'll continue with dz dx after that. Okay, let's plug in the bounds. So it's minus x squared cosine of xz, and then it's going to be minus minus, which is plus x squared cosine of 0 dz dx. Moving along, cosine of 0 is z1. We're going to have then x squared minus x squared cosine of xz. And now let's prepare to integrate with respect to z. Okay, you may want to actually pause and go a little bit slower, or do this on your own. Here we have to really pay attention to the partial antiderivatives. At this stage in the game, x is a constant. So therefore, the integral of x squared is going to be just x squared z. And minus x squared times the integral of cosine of xz, that requires like a u substitution for xz, right? The variable is z. So the integral of of cosine is going to be sine of xz, but I'm going to have to divide this guy by x to compensate for that chain rule, right? So if I, if you go in reverse, if we differentiate sine, I get cosine of xz, but there's also times x because of the chain rule, so I have to put an over x to cancel for that. So anyway, that's the antiderivative for the middle integral with the bounds for z between 0 and x. Again, if it's not clear what I did here, you can take apart the antiderivative of cosine of xz dz and just do a little u substitution for xz. Remember, your variable of integration is z. So that's why you move the x over to the left. Okay, let's continue with this. We're gonna plug in x and 0. When I plug in 0 for z, is gonna be 0 minus 0, so I'm not gonna bother with that. So therefore, the last piece to integrate is gonna be x third minus x squared over x is just x times sine of x squared. Of course, it's made to work because there is another u substitution here. If you look carefully, this x on the outside of sine is just right, because the integral of sine is, again, minus cosine over, so minus cosine of x squared over x. So that's just, we'll cancel with this existing x. Or again, if it's not clear, on this stage here, you're going to take u to be x squared, du is 2x dx. So it's going to be du over 2, right? So let's see. Antiderivative is x fourth over 4 plus cosine of x squared divided by 2. Okay, because that piece, that second piece, it will be the integral of sine of u du over 2, right? Which is minus cosine, but there's another minus, and that's why it becomes plus cosine of x squared. Okay, everything between 0 and square root of pi. So square root of pi to the 4, that's pi squared over 4, 1/2 cosine of pi, and then plug in 0. I get pi squared over 4 minus 1/2 minus 1/2 pi squared over 4 minus 1. Okay, so we're gonna do two more just to see variations of these types of problems, and yeah, not much to say, just two more, because we need to have, there are, like I said, the idea is the same, but in some cases you're gonna have to do some preparation work in terms of sketching. So these problems could be quite long. That's why in many exams sometimes you are given just as a task just to set up the integral and the correct bounds, which is also enough work on its own. So let's stay tuned for two more examples. All right, so in this one we're gonna compute the integral of z dv. So notice I chose a simple function so that I won't waste too much time with the actual integration, not too much at least. And again, I'm going to focus on how this blends with what we did before. And then let's say the solid E is defined to be the region bounded, the solid bounded by the paraboloid z equals 4x squared plus 4y squared, and the plane z equals 4. This one requires a little bit of sketching in order to set it up. Again, I want to emphasize that those, because sometimes my students say, well, okay, I mean, why do I bother with this? Because the calculator will do everything for me. I mean, if you look at Maple and you choose the triple integral, Maple expects you to actually fit the bounds to it. So, like, you know, often this is the tricky part. So you are still responsible to actually give the parameters to the calculator or to the computer. Now, you could also sketch. Of course, I mean, the sketching is much easier. I mean, you can sketch, for example, with Maple or something similar, but you still have to figure out the bounds kind of on paper together with the aid of the computer. All right, so we have a paraboloid opened up. So let's see how we can sketch it. always do just enough sketch to make to have an idea, and not too much, because usually in 3 dimensions, if you try to put many details, it usually makes the picture worse. So this is the paraboloid opened up, starting from 0, 0, 0, and then z equals 4 is the top here on, at this level. So it's going to obviously cut the paraboloid. It's going to be a circle. In general, it can be an ellipse, okay? But this is essentially the trace, okay, of the plane that cuts through the paraboloid. Okay, so let's actually kind of emphasize the solid here by making the a little bit thicker, these margins here. Okay, so we now move to the Fubini's theorem part of it. To apply Fubini, remember you need to see the object, the solid E, as between a top and a bottom given by 2 surfaces with the same domain. So the top, obviously, it's the surface z equals 4, which, remember, you can view it as a function of 2 variables. No problem with that. The bottom is going to be the paraboloid itself. Okay, so remember, for the Fubini theorem, the entire solid should be represented by this, what I like to call jokingly in class, spaghettification of the domain, basically. So if you can actually exhaust the domain by pulling these spaghettis, that is to say, you have each piece between the same 2 surfaces given by the same equations, then the Fubini's theorem can be applied. And then the bottom bound is going to be given by the paraboloid itself, 4x squared plus 4y squared. So that's going to be the lower bound of z. Okay, so I know already, by the way, that my triple integral is going to split into a double integral and an innermost integral from 4x squared plus 4y squared all the way to 4 dz. And then the function to integrate, of course, is z. Now, what is the common domain? Okay, the common domain, obviously, if I see it from above, is going to be whatever this intersection projects onto in the xy plane. This is the common domain of the top and the bottom. How do you find it? Well, I'm going to have to intersect the 2 surfaces and eliminate z. So if I set the 2 surfaces equal to each other and divide by 4, I get a circle, which means the domain is the disk represented by the x squared plus y squared equals 1. It's a solid, right? So it projects not just on the circle, but on the interior of that disk, of that circle. Because you anticipate you're going to do a double integral, it might be worthwhile to sketch the domain separately in x and y, the common domain of the 2 bounds for z. So this is a circle of radius 1. Okay, at this point you have all you need to proceed with the triple integral to the Fubini's theorem. So let's do it one more time. The triple integral of z dv is going to be the double integral over this common domain of whatever I get from the innermost integral, which runs from 4x squared plus 4y squared all the way up to 4 z dz dA. We have to do the innermost integral before you worry about how you solve the double integral on the outside. Okay, the innermost integral shouldn't be too much of a problem, right? It's z squared over 2 with the bounds again 4x squared plus 4y squared and 4. Plug in the bounds. That's 16 over 2, 8 minus 4x squared plus 4y squared squared over 2 dA. Okay, let's pull up those constants to clean up a little bit this. So it's 8 minus, outside of this square is going to be 16 over 2, that's another 8. And you're left with x squared plus y squared quantity squared dA. Okay, so now we are in the realm of double integrals. We're done with the innermost integral. How do we solve the double integral? That remains. Now we look at the domain and we act accordingly, right? In this case, the domain is a disk. I see the x squared plus y squared here. Should be pretty obvious at this point that polar coordinates are the way to go. In polar coordinates, remember those identities. In the polar bounds, the domain, obviously, it's a full disk. So the bounds for theta are 0 to pi, and for the polar radius, 0 to 1. So this becomes the integral from 0 to 2 pi, and then from 0 to 1. The stuff to integrate is 8 minus 8 r squared squared, which is r fourth. And of course, don't forget that dA becomes dr d theta. Split the integral into a product. And if we multiply by this r, that's 8r minus 8r to the fifth. By the way, I know I go fast, I strongly advise you to actually pause anywhere you want and do these calculations, especially this double integral. Do this on your own, it's extremely useful, and then you can run the movie and then see if you got it right, just as a matter of practice. Okay, the first integral is going to be 2 pi, we've seen that before, so we just write 2 pi, and then the one in r is going to be 4r squared minus 8 over 6 r to the 6 between 0 and 1 makes it 2 pi times 4 minus 8 over 6 24 minus 8 that's 16, no, 24 minus minus 8 yeah, that's 16 on the top, and then we can simplify this by 3 by 2, and then the answer is 16 pi over 3. Okay, so one more example which kind of again has kind of everything, not overly difficult at any given step, but lots of little intermediate steps. Not many of them are like that, but these are very useful at this stage in the game, because again they will kind of go, put you through lots of earlier concepts in the course, which is always useful. So stay tuned for our last example. Okay, so our example, let's find the triple integral of xyz, and the this one, actually, in this case, to save some time, in fact, we're gonna probably just set it up. We'll see. I'm gonna give you the answer anyway, but let me think a little bit. I don't think it's gonna be well. I'm gonna do maybe we'll see. I'm not gonna turn another page. I'm gonna do some of it, and give you the answer and leave the remaining part as an exercise if it doesn't fit. Because the whole point is to actually focus mostly on the setup. So the solid in question is the tetrahedron connecting the points 0, 0, 0, 1, 1, 0, 1, 1, 1, 0, 0, and 1, 0, 1, right? So the tetrahedron is the solid where each side is a triangle, right? Which means that it can be defined by 4 points in space. So you see, in this case, you don't even have the equations of the faces representing the solid, right? So you kind of have to start from scratch, which is the reason why we learned some of the geometry aspects in the beginning of the class. So let's start with actually visualizing this solid. So 0, 0, 0 is obviously the origin, and 1, 0, 0 sits on the x-axis. So let's say it's over here. I'm going to try to make it not too cluttered here. And then I'm going to say, let me make it like that. I'm going to say like this is, let's say this is over here. the point 1, 1, 0, and then the third one, which is 1, 0, 1. So x is 1, y is 0, so it's over here. So it's in the xz plane all the way up to this point here. Okay, so this is 1, 0, 1. Okay, so if I were to actually sketch this, I mean, to emphasize the see if it looks nice. Doesn't look too pretty. I have this overlap which I don't like, but let me see. I think it's good enough. Okay, there's the tetrahedron. Sometimes you kind of have to distort the image to actually visualize all faces here, but I think that's good enough. The important thing is to see it as a top and a bottom cover in order to apply the Fubini's theorem. So this is the point 0, 0, 0. Okay, so for the purpose of Fubini's theorem, you can, and by the way, the top and the bottom with the same common domain. So the top is going to be the face connecting 1, 0, 1, 0, 0, 0, 1, 1, 0. Obviously, that's going to be a plane, so it's my job to actually write that plane as an equation in x and y, because that's going to be my upper bound. Because clearly, you see, this line here is vertical line, the one from 1, 0, 1 to 1, 0, 0. So this top plane that I talked about, this triangle, projects onto the bottom triangle, which becomes the common domain. So the bottom of the object is pretty straightforward, right? That's z equals 0, right? So that's the lower bound of the innermost integral. That should be pretty straightforward. And then the common domain is going to be, so the common domain of u1 and u2 is going to be the triangle connecting the points, and the interior of the triangle connecting the points 0, 0, 0, 1, 0, 0, and 1, 1, 0. Okay, so I hope it's pretty clear. Let me actually show you one typical vertical slice or spaghetti, if you want, right? Connecting a point on the top and a point on the bottom, right? So this is going to be the upper bound z equals u2 of xy, which is yet to be determined, and the bottom is z equals u1 of xy, which obviously is 0, right? It's z equals 0. Okay, so what is the next task for this problem? Well, the next task is to get that plane as a function of x and y. We have 3 points on the plane. How do you make the equation of the plane? Well, we have the normal vector equation of the plane, right? We need to come up with the normal. So the normal to the plane. For that, we need 2 vectors. Let's make the vector from 1, 0, 1 to, well, actually, it's pretty easy in that case. I mean, because we already have 0, 0, 0 as one of the points. So I can consider already the vector from the origin to 1, 0, 1 as a vector in the component form. And another vector from that point from the origin to 1, 1, 0. So the normal of this plane, which is u cross v, let's do the cross product. That's 0 minus 1, the first component. And then middle component, let's see, 1, right? 1 times 0 minus 1 with another sign change, that's 1. And the last component is 1 times 1 minus 0, which is 1. So the normal is minus 1, 1, 1. And to make it easy, just using the origin actually as one of the points on the plane. So we're going to have the equation of that plane, minus 1 x minus 0 plus 1 times y minus 0 plus 1 times z minus 0 equals 0. So that's minus x plus y plus z equals 0. And as a function of x and y, that's x minus y. Okay, so the upper bound on that triple integral is going to be x minus y. So I know that my triple integral is going to be between, for z, between 0 and x minus y. So I know that my triple integral is a double integral over that common domain, the triangle on the bottom. And the innermost integral is from 0 to x minus y, x, y, z, dz, and then dA. Now we have to figure out how we compute the double integral on the outside. Okay, as always, remember it's useful to take that domain apart in the one second, I want to check something before I move on. So the domain for the xy part, I mean the common domain of u1 and u2. Yeah, let's take it apart and sketch it in the y-x plane. Because again, remember, we need to split this using Fubini's theorem for this double integral on the outside. And in this case, it's really useful to actually visualize it in the plane, so you can decide whether you do it as a type 1 and type 2 domain. So once again, the triangle is made of the points, now we ignore the z-coordinate, right? It's made of the point 0, 0. Another point is 1, 1 over here. And another point is on the x-axis, which is right here, 1, 0. You can choose type 1 or type 2, doesn't matter. You have to compute the equation of the line connecting 0, 0 and 1, 1, but that's pretty obvious. That's y equals x. So let's say I want to view this as a type 1 domain, which means let's say I want to go by the x coordinate on the outside. So finally, now my triple integral is going to be bounds for x on the outside, the constant bound 0, 1. Now the innermost bounds for y run from y equals 0 to y equals x. And then finally the innermost integral from 0 to x minus y, x, y, z, dz, dy, dx in this order. So I hope you guys appreciate that you need to be kind of slow in the beginning and meticulous in order to set up the correct integral. From this point on, of course, you could use it, you could do Maple or anything, or Wolfram Alpha, whatever you like, because once you feed in the bounds, then the computer will do it for you. The answer should be 1 over 144. I don't actually remember if it's actually that doable. Like I said, I'm not going to turn the page because it's enough for this class, but let's just do, for the sake of it, just a couple of steps. The innermost integral, z is in z, that's going to be xy z squared over 2. I can tell already it's not going to be that pretty, so we'll see. So from 0 to x minus y for z. Or maybe it is, I don't know, let's see. And now I plug in x minus y to the power 2. So I have to expand that before I continue with the integral. That's x squared minus 2xy. So this parenthesis is x squared minus 2xy plus y squared. And we can pull the 1/2 out just to get it out of the way. And so I'm left with, let's see, x third y. The middle term becomes minus 2x squared y squared. And then the last one plus xy third. And now I do dy dx. Now I integrate with respect to y. And I get x third y squared over 2. One of the good things about this is that once it's recorded, I don't have to do it one more time. And then minus 2x squared y third over 3. And then plus xy fourth over 4. And now, of course, the bounds are 0 and x. I think it might be doable, actually, because the powers are the same now. Let's see. Now I plug in x, 0 doesn't matter. So when you plug in x, actually that's going to be x fifth over 2 minus 2 over 3 x fifth 1/4 x fifth. So there's another giant constant that comes out, 1/2 minus 2/3 plus 1/4. And then the integral of x fifth is going to be x to the power 6 over 6 between 0 and 1, which is just 1 over 6. So on the top here, let me put it here as this corner has a scratch paper. So I have 6 minus 8 plus 3. That's like 9 minus 8, which is 1. So the constant is 1 over 2, 1 over 12, and then 1 over 6 from plugging in 1 and 0. And yes, that's it. So we manage it. So 1 over 144. Okay, so I think enough integration for today. I'll see you next time. The last topic on the unit will be triple integrals in spherical coordinates. I'll skip the cylindrical coordinates for a reason I'll explain when the time comes. Next lesson. See you later.